What's up, mathematicians? Justin here, and in this video, we'll be taking a closer look at our axiomatic system for geometric constructions. Now, in the first lesson in this unit, we looked at the tools for doing geometric constructions, right? The compass and the straight edge. And then in this lesson, we've been focused more on the rules. But in this video, I want to take a little bit of a broader look at the system that we're creating here, give a bit more context and look in a bit more detail at the different parts of the system. So let's take a look at the parts of the system. I went ahead and drew the diagram from the last video to make it a bit more clear. And so let's go through the different parts. First of all, we have the ground, and this is not the foundation for the system. It's below the foundation. It's the ground that the foundation is embedded or grounded in. And the things that make up the ground are logic and language, as we discussed in the last unit. Basically, I'm just going to assume that we all know how to use the rules of logic and we're all speaking the same language. Furthermore, we're going to say that we have a sheet of paper. Anytime we need to do geometric constructions, we're going to, do them on a sheet of paper or some sort of flat surface in general. But in these videos, we'll be doing them on paper. And that sheet of paper is useful for drawing diagrams and constructions. So that's the ground. Now, the next level up. Here we have the foundation, as I call it. Foundation has two main parts. Number one are assumptions. Number two are definitions, assumptions and definitions. So first of all, we have these rules, and these rules are assumptions. By saying you can draw or define a point anywhere, I'm assuming you can actually do that. By saying you can extend a line, I'm assuming you have the ability to do that. You have a tool for doing that. And of course, in the case of geometric constructions, our tool for extending a line is the straight edge. So that's one part, the assumptions. I'm also leaving some space here for other assumptions beyond the rules. We'll fill these in future videos. Okay, and then we have the definitions. So I'm not going to write all these out. There are many, many of them. These are things like triangle, circle, square, whatever. All these things that we have pretty specific mathematical definitions for. And I'll be using the typical definitions for these things in this unit. You can look them up wherever you look things up. One quick exception to that, me using the sort of typical definitions is I'm going to take equal and congruent to really mean the same thing. This is in keeping with the way the ancient Greeks approached the concept of equality, although I'm sure some people will take issue with it, and if you look at textbooks, you'll see that they have a separate designation for equal and congruent. But basically, we're going to just say that if two objects have identical size and shape, we'll go ahead and say they're equal, and understand that equal doesn't necessarily mean they're in exactly the same location. Okay, so that's our foundation. Part number two. Now let's move on to part number three, which is the bricks. Okay, the bricks are facts that have been proven to be true within this system. Within this ground, or on top of this ground, built on this foundation, all these bricks are true. They're facts. Okay, now keep in mind, they should not be thought of as being universally true. All these bricks, I'm not saying that all these things are universally true. What I am saying is they are true within the context of our system. Okay, and mathematicians call these bricks, these proven facts, they're called theorems. So I'll be referring to them as bricks and also as theorems. Those terms will be interchangeable in this unit. But in terms of the structure, the sort of analogy that I'm using, the theorems or the facts are the bricks. Okay, so those are the three parts. We have the bricks, we have the foundation, and we have the ground. Now, what have we proven so far? Okay, well, first of all, we have proven that we can construct a triangle. And therefore, since we can construct a triangle, triangles in fact exist within our system. Pretty cool, huh? Now, I can see some of your maybe skepticism here, or just like, really, are you gonna push it to that level? Yes, I am. Okay, so it may seem obvious to you that because we have a definition for a triangle, so of course they exist, right? A triangle is a three-sided shape where all the sides meet at the 3 points of the triangle. The problem is it's not logically necessary that something exists just because we define it, okay? So for example, I could define a unicorn. I could say a unicorn is a horse with, a horn on its head. Maybe that's not a very specific definition, but you get the idea. But just because I make a definition for unicorn does not bring unicorns into existence. Okay, we can't just define things into existence. So we need our definitions, of course, but we just because we define something doesn't mean it exists. We still have to go through the process of proving it. A more mathy example of this might be, let's think about the definition of a right triangle, for example. And I'm even going to draw one here. So let me use my straight edge and draw it nicely, make it nice and pretty. Okay. So here, and I'm not constructing this as a right angle. I'm just going to go ahead and use the dots on my paper. Okay, so what is a right triangle? A right triangle is a triangle with one right angle. And I've drawn one there. And you probably know this. But now imagine I were to define something else, another concept. Imagine that I were to define a really right triangle as a triangle with all three angles being right angles, okay? So just because I have a definition does not mean that really right triangles exist. I mean, try drawing one on this sheet of paper. Basically, I can draw a couple of right angles here. Okay, but if I look at this, it certainly doesn't seem like these two lines are going to meet up and make the third point of a triangle. And even if they did, maybe somewhere way off the end of that paper, it certainly doesn't seem like they'll come together to make a right angle. So a really right triangle, a triangle with all right angles, just because we have a definition for it doesn't mean it exists. Okay, so you may feel I'm being a bit meticulous or pedantic by proving triangles actually exist when their existence seems obvious, but we will see later that even in the case of the square, issues of existence will come up. So to reiterate, we have proven in the system that triangles exist. And that's a good thing, because our main goal is to prove that the angle sum of a triangle is 180 degrees. And the existence of triangles is going to be really helpful in being able to prove attributes about triangles, like their angle sum. So that's the first brick. And then the second brick is we proved that we can construct an equilateral triangle, which means equilateral triangles exist. Yay! All right. So what do we want to prove? Now, we need to think about what do we hope this system will be powerful enough to produce. There are three big theorems that I would like to prove, that we would like to prove in this system. The first one, and the most important, is the angle sum of a triangle. We want to prove that the angle sum of a triangle is always 180 degrees. The second one is that the corresponding sides of similar triangles are proportional. Those two, the angle sum of a triangle and the proportionality of corresponding sides of similar triangles, those are things that we relied on when we did trigonometry in our first unit on measurement. A third one that we'd like to do, which is also really helpful for measurement, is the Pythagorean theorem. So if we could do those three, angle sum of a triangle, proportionality of corresponding sides of similar triangles, and the Pythagorean theorem, that would be great. That'd be like the trifecta of theorems that give us the power to create really powerful tools for measurement. Okay, but as I mentioned already, of course, the number one goal, angle sum of a triangle. Okay, so before we wrap up this video, I want to spend just a minute talking about why do I emphasize this axiomatic system so much. And it really comes down to this, to the fact that I hate the way that proofs are often taught in high school geometry. I hate the way they were taught to me and how they're still being taught to many students, even now 25 years later. In a typical high school geometry class, you'll have a unit on proof. I mean, what do you do in that unit? Let's think about it. It's like the teacher or the textbook, whatever, will say, okay, here's some contrived situation, and here's a bunch of, facts that you can use along with logic to resolve this situation. Like, okay, prove that this angle over here is equal to that angle over there. Who cares? The thing is, what we're having students do is really just a bunch of logical exercises, which by itself, maybe doesn't seem like such a terrible thing, right? I mean, logic exercises can be fun, but it doesn't give students an understanding of the structure of geometry or the structure of mathematics in general. Students don't come out of that unit on proof, with a real understanding of what it means to actually prove something. What does that mean? Once you prove something, is that thing true? What does it mean? Like, in what sense is it true? In what context is it true? And so, my concern here is, you don't really understand Euclidean geometry if you don't know anything about the structure. You may be able to do some measuring, find the area of this shape or what have you, but you don't really understand the structure that you're working in, the system that you're working in. Textbooks, generally speaking, do a pretty bad job of communicating this structure if they mention it at all. And teachers often don't understand the structure themselves either. So by focusing, in taking my approach, by focusing on this axiomatic system explicitly, you'll come away with a much better understanding of and appreciation for the structure of the system, how rigorous and powerful and robust it is. Okay, deep breath. So that's my rant about how geometry is taught, and so that'll wrap up our lesson for today. But remember, if you want to learn, you need to practice. Okay, practice problems will be down below in the description. Thanks for watching, and I hope to see you in the next video.